Welcome to our channel Interesting Engineering. Let's discuss about Gall Tinsley coordinate potentiometer. So this is a AC potentiometer which measures unknown voltage in terms of two components V1 and V2, where V1 is the in-phase component and V2 is the quadrature component, and the resultant unknown voltage is denoted by V, and it can be calculated using the equation V is equal to root of V1 square plus V2 square. So this is the structure of Gall Tinsley potentiometer. So here we could see two potentiometers, in-phase potentiometer and quadrature potentiometer, enclosed in a single case, and these two potentiometers are supplied with a AC voltage, and that AC voltage is applied to these two potentiometer by through a step down transformer. So step down transformer is used here, and it has two main functions. One is it is meant for reducing the AC voltage up to 6 volts, and the second purpose is to isolate the AC source from isolate the potentiometer circuit from the AC source. That is, the AC source will be having a more voltage level, so that voltage level is being could affect the potentiometer circuit. So in order to avoid such problem, it is being isolated from the circuit by means of isolation transformer, that is nothing but the step down transformer used here, and it supplies the AC voltage through these two terminals. So here this in-phase potentiometer is a resistive circuit where the working current, where the voltage developed across the sliding contact is directly proportional to the working current, and here this quadrature potentiometer is supplied by means of a phase splitting device. So here we could have a resistor, series combination of resistor and capacitor circuit, which is meant for having a quadrature arrangement, that is the whatever voltage here the current through this quadrature potentiometer will be will have a some phase difference compared to this in-phase potentiometer. The magnitude of working current through these two potentiometer will be same, whereas the phase angle, there will be a phase difference. So to create that phase difference, we have a series combination of resistor and capacitor circuit, and these two are the sliding contacts of the potentiometer, where B dash and C dash are the sliding contacts. So this the potential developed across this B dash axis V1, and potential developed across C dash axis V2. So the combination of V1 and V2, since this is connected in directly with the unknown voltage. So this unknown voltage is connected in series opposition with this these two terminals. The resultant voltage will be V1 plus JV2, and here we have a ammeter, electrodynamometer ammeter. This is meant for measuring the working current through the potentiometer circuit, and since this is a AC potentiometer, we have a vibration galvanometer here instead of D'Arsonval galvanometer. So this vibrational galvanometer is tuned to a particular frequency, and this is for detecting the null balance condition. And here we have three selector switches, S1, S2 and S3. This S1 and S2 acts as a sign changing selector switch, and S3 acts as the selector switch for making for operating this entire circuit under three different operating conditions, that is standardization, testing and working condition. So measuring condition. So this is the selector switch which makes the entire circuit to operate under three different conditions, and through these two terminals we pass the unknown voltage that is to be measured. So this is the structure of a Gall Tinsley coordinate type potentiometer, and regarding its operation, So regarding its operation, it will be operated under three different conditions: standardization, test and measure. So standardization, as we all know, for before making use of any instrument, we must standardize that instrument first. So for that purpose we make use of the standardization, and here the selector switch S3, when it is connected at this first point, it the entire circuit operates under the standardization. So here, when the standardization terminal is being connected over here, we make use of two main changes here. So here the in this voltage terminal we connect a standard cell, and here the vibration galvanometer will be replaced by a DR-Sunwell galvanometer, and standard cell will be supplying a potential of about 1.0186 volts. So the standard cell, the operating condition during standardization, when we connect a standard cell here, it will be supplying a voltage of about 1.0186 volts. At that condition, here we will be replacing this vibration galvanometer by means of a DR-Sunwell galvanometer, and the sliding contacts are adjusted and placed at a particular position. At that particular position we measure the working current. So this working current is measured for a null balance condition of galvanometer. So for the particular position of sliding contacts, we should achieve a zero null balance condition at the galvanometer. So when to achieve this null balance condition, we adjust the rheostats here. So these rheostats are for adjusting the working current through the potentiometers. So R and R dash rheostats are adjusted to achieve a null balance condition for a predefined position of the sliding contacts. So at that position, when we achieve a null balance condition over here, we measure the working current through the potentiometer. So it should always be maintained at suppose it is maintained at 50 amperes. So this is the standardization operation. That is, during standardization we connect a standard battery cell supplying a voltage of about 1.0186 volts, and during standardization we replace the vibration galvanometer by a DR-Sunwell galvanometer. So this 1.0186 volt is placed positioned by means of these two sliding contacts. So for these two sliding contact position, we should achieve a zero condition in the galvanometer. Suppose if it is not achieved, we have to maintain a zero condition by means of adjusting these two rheostats. So while adjusting the rheostats, we should achieve a zero condition for a particular position of the sliding contacts. So when we achieve a zero condition in the galvanometer, the current through the potentiometer is being measured, and it is measured by means of the electrodynamometer ammeter used here. So it is normally maintained at 50 amperes. So it is being measured, and it should be maintained constant during its operation also. So it has to be maintained constant. That is, the working current should be maintained constant throughout the entire operation of the potentiometer circuit. So this standardization of working current is being done during the standardization operation in the potentiometer. Then the next operation, the next thing is to test. So testing. So in testing we make use of a mutual inductor. placed across the quadrature potentiometer. That is, the quadrature potentiometer, the working current through the quadrature potentiometer has to be similar to that of the current through the in-phase potentiometer, but it has to be maintained. It has to it should have a phase difference of 90 degree, so that we have to check using this testing condition. So during testing condition, the selector switch is maintained at a next position. That is, in the previous case we maintained the selector switch at the first position for standardization. Then during testing condition, we have to change the selector switch to the second position, and then here we place a mutual inductor connected and mutually across the quadrature potentiometer. So in the case of mutual inductance, there develops a potential E. So E is calculated by 2 pi E is equal to 2 pi f I into m. So here 2 pi f and m are all constants. So depending upon the working current, that develops a potential here. So in the initial case, suppose initially there flows a current I through the in-phase potentiometer, and this current I1 will be the current through the quadrature potentiometer will be leading this current through the in-phase potentiometer by 90 degree. So this I2 will be developing a potential E. So this, due to this E, there develops due to the passage of current I1 here, due to the passage of current I1, there develops V1. So this V1 and I1 will always be in phase in the case of in-phase potentiometer, whereas in the case of quadrature potentiometer, the current through the quadrature potentiometer will always lead this voltage developed in the quadrature potentiometer by 90 degree. For this condition, we have to check. So that is being tested by means of connecting a mutual inductor here, and this voltage by means of voltage developed across this in-phase potentiometer and the quadrature potentiometer, we can able to test the entire circuit. So this is the testing operation of this Gall Tinsley potentiometer. So this is the equation used for calculating the potential developed in a Gall Tinsley potentiometer. So using this equation, we check for the voltage drop across these two potentiometers V1 and V2. So when these two are in they have a quadrature, they have a phase difference of 90 degree, the quadrature potentiometer's operation is under good operating condition that we can analyze. Then we go for the next operating condition of this potentiometer, that is nothing but the measure. So in the initial case, we discussed about standardization, where we standardize the potentiometers for the working current by adjusting the adjustable rheostats R and R dash, and in the next case we tested the quadrature potentiometer operation by means of analyzing the potential developed across the sliding contacts B dash and C dash, then whether it has a 90 degree phase angle difference. Then we go for measurement condition, where the selector switch is placed at the third terminal, where we are connecting the unknown voltage here. So this unknown voltage is connected over here. So here based on the unknown voltage, there is a the working current, these two working currents are maintained constant. In phase and in phase and quadrature potentiometer working currents are maintained constant, and now based on the application of unknown voltage, that we have to adjust the sliding contacts B dash and C dash. So when B dash and C dash are adjusted, we need to achieve a zero condition in the galvanometer. When it is achieved, so for null balance condition of galvanometer, what is the position of B dash and C dash? That represents the measurement of unknown voltage by in terms of two components, V1 and V2. So the potential developed across the contact B dash represented by V1, and potential drop developed across C dash is represented in terms of V2. So by means of V1 and V2, we can able to measure the unknown voltage across this terminal. So this is about how to measure the unknown voltage. So in the initial case, we need to standardize the instrument, then we have to test the instrument for quadrature potentiometer, and in the last case we can able to measure the unknown voltage by adjusting the sliding contacts. So by means of two voltages, V1 and V2. So V1 plus JV2 represents the unknown voltage, capital V. So by means of which we can able to measure the unknown voltage in the case of Gall Tinsley AC potentiometer. So I think I'm clear. So with this Gall Tinsley potentiometer is over, and in our next video we shall discuss about instrument transformers. So for more videos, keep watching. Please subscribe and share. Thanks for watching.